In this video, I'm going to tell you how I remember the different fractions that go with each of these terms: molality, molarity, and mole fraction. Notice that molality and molarity only differ by a single letter, an R or an L. The way I remember molality is that L is the closest letter of the two, R or L, to the letter M, and M stands for mass. And in molality, the bottom of the fraction has to do with mass. The lowercase m should be italicized. I can't write it very well italicized, but it's the same symbol as we often use for mass. Now, both molarity and molarity have to do with moles of solute on the top of the fraction. If we have mass on the bottom of the fraction, it's going to be kilograms of solvent. Molarity does not have the letter that's closest to M, and therefore it's the one that does not have to do with mass. So molarity uses the capital M symbol, which is not the symbol for mass. It also is italicized. Again, moles of solute are on the top, but this time volume is used on the bottom, liters of solution. A mole fraction is the easiest of the three to remember, except that its symbol is a little bit random. It makes sense for a mole fraction that moles would be on both the top and the bottom, since it's a fraction made of moles. A capital X is the symbol. I don't know why. The top has the moles of one component. The bottom contains the number of moles in total in the solution. The top of this fraction could be used for any of the components, the solute or the solvent, in the solution. The number on the bottom will always be the total of all of the moles together, usually found by using addition. One thing that's important to mention when we have moles at the top of a fraction is that moles often have to be found when we are given grams by using the fraction 1 mole equals the molar mass of any molecule or element. Now let's try problem number 9 on page 2 of your week 16 homework. The problem reads, what is the molarity of a solution prepared by dissolving 16 grams of barium chloride in enough water to give 450 milliliters of solution? When we do these, please have your homework sheet out and read along with me. I expect to see all of the work showing on your homework sheets. We are given 2 bits of information, actually 3. One is the term molarity, which is the one with the R in it. The R is not the closest to the letter M, so we're going to use a capital M as the symbol, and the fraction is moles of solute per liters of solution. We're also given the fact that we have 16 grams of barium chloride. Barium chloride is being added to water, so we know that barium chloride is the solute. Therefore, somehow we have to get 16 grams of barium chloride at the top of this fraction as moles. So the first thing we're going to do is convert 16 grams of barium chloride into moles. We'll do that by multiplying by a fraction that has equal amounts on the top and the bottom. We know that 1 mole of anything is equal to its molar mass. So we'll use a fraction which has 1 mole at the top and the molar mass of barium chloride at the bottom, which is given in grams Therefore, the grams will cancel one another. By now, you should know that the molar mass is the sum of the masses of each of the individual components in the molecule. So we add barium, which weighs 137, and 2 chlorines, which each weigh 35.5. Adding those together, we get 208. When we divide 16 by 208, we get 0.077 moles of barium chloride. The next bit of information we're given is 450 milliliters of solution. We know that in order to find molarity, we need liters of solution at the bottom of our fraction. So we need to convert milliliters to liters. We do that by dividing 450 by 1,000, since there's 1,000 milliliters in 1 liter. We get 0.450 liters. Now, we'll substitute these numbers into our molarity fraction. .077 moles of barium chloride divided by 0.450 liters of solution leaves us with a molarity of 0.17. Please always circle your answer. That makes it easier for me to correct it. Now let's try problem number 10 on page 2 of your week 16 homework sheets. The problem reads, what is the molality of a solution, a solid solution containing 0.125 grams of chromium and 81.3 grams of iron? We notice that the word molality is used. Molality is the one with 2 L's. L is closest to M. Therefore, we know it's going to be the one involving mass. Molality is moles of solute divided by kilograms of solvent. Now, we notice this is a solid solution. We're given 2 parts of the solution, chromium and iron, but which one is the solute and which is the solvent? Well, most likely the solute is going to be the smaller amount. The solvent is going to be the larger amount. So we're going to consider chromium, the solute, and iron, the solvent. So we need 2 different units for each of our components. We need to find chromium as a mole unit, and we need to find iron in kilograms. Let's start with chromium. Our problem tells us that we have 0.125 grams of chromium. We know that the molar mass of chromium is 52 grams. We know that by looking at its atomic weight on the periodic table of elements. Now we have to take 0.125 and divide it by 52. Now we know we have 0.0024 moles of chromium. Our problem also tells us that we have 81.3 grams of iron. We need to convert that to kilograms. We put grams on the bottom so that this unit and this unit cancel out and we're left with kilograms, which is what we're looking for. So 81.3 divided by 1,000, the answer is 0.0813 kilograms of iron. Now we'll be able to substitute these numbers into our molality fraction. And we find out that the molality of this solution is 0.0295. Now let's try number 13 on page 2 of your week 16 homework sheets. The problem reads, what is the mole fraction of each component in a solution made by mixing 300 grams of ethanol and 500 grams of water? First, we know that the mole fraction is what we're looking for. That's a fraction with moles on the top and moles on the bottom. The symbol for mole fraction is X. I changed the wording slightly, moles of part to moles of whole. It means the same thing as moles of component to moles total in the solution. Now this question asks for the moles of each component. So we have two components. We have ethanol and we have water. Since our units are in moles, we have to convert both of our components to moles. We see that 300 grams of ethanol divided by 46, which is its molar mass, equals 6.52 moles of ethanol. We see that 500 grams of water divided by 18, which is its molar mass, is 27.8 moles of water. Now, we need two answers. We need to find the mole fraction of each component. Let's start with the mole fraction of ethanol. The mole fraction of ethanol has the moles of the part, which is ethanol is the part, so we take 6.52 moles of ethanol on the top of the fraction. Then the moles of the whole, which is found by adding the moles of ethanol plus the moles of water, so 6.52 plus 27.8 on the bottom of the fraction. Now when you do this on your calculator, you need to do the adding first, find what the number is on the bottom, and then do your division. Or you can put the addition part in parentheses on your calculator. You can put 6.52 divided by, and then put a parenthesis, 6.52 plus 27.8, and your parenthesis, and then equal. It's important that the adding is done first. And we see that the mole fraction of ethanol is 0.190. Next, we'll find the mole fraction of water. You take the number of moles of water at the top of the fraction, the moles of the whole, which I added together this time, 34.32 on the bottom of the fraction. Do the math, it comes to 0.810. Let's look at number 14 now on page 2 of your week 16 homework sheets. It reads, what is the mole fraction of each component in a solution made by mixing 50 grams of carbon tetrachloride and 50 grams of chloroform? We know that we're using mole fractions, and I already have the mole fraction equation right here. We're given two different components, 50 grams of carbon tetrachloride and 50 grams of chloroform. In order to put these numbers into the equation correctly, we need to convert them to moles. For each of our components, I've multiplied by a fraction which has 1 mole on the top and the molar mass on the bottom. And it turns out we have 0.325 moles of carbon tetrachloride and 0.418 moles of chloroform. Now we need to find the molar fraction for each of our components. So we'll substitute these numbers into the molar fraction equation. So the molar fraction for carbon tetrachloride has the number of moles of carbon tetrachloride on the top, because that's the part we're asking for, has the sum of the number of moles of both parts of the solution on the bottom. Again, if you're going to put this into your calculator, this sum needs to be in parentheses. When we do the math, it comes out to 0.473 for carbon tetrachloride. For chloroform, we have the number of moles of chloroform on the top, because that's the part we're looking for. We have the total of the whole solution on the bottom, total number of moles. When we do the math, we get 0.563. Let's look at number 17 on page 3 of your week 16 homework sheets. The problem reads, what is the molarity of the solution produced when 145 grams of sodium chloride is dissolved in sufficient water to prepare 2.75 liters of solution? Now, before you listen to any more of this, please stop the program and try to do it yourself, and then check yourself by watching my work. See that the problem asks for molarity. Molarity is the one with the R in it. That's not close to the letter M, so we use the large M for the symbol for molarity, and we know that it's moles of solute divided by solution, liters of solution. What we're given is 145 grams of sodium chloride, which is the solute. We know that because it's being dissolved. In order to turn the units of grams of sodium chloride into moles, we have to multiply by 1 mole over the molar mass of sodium chloride, which is 58.5. When we divide 145 by 58.5, we get 2.48 moles of sodium chloride. We are given that the solution contains 2.75 liters, so we don't have to do anything to change liters for the bottom of the fraction. Now let's substitute our numbers into the equation. So the molarity of this solution is 2.48 moles of sodium chloride divided by 2.75 liters of solution. Comes out to 0.902 moles per liter. Now let's try number 18 on page 3 of your week 16 homework sheets. It reads, what is the molality of a solution containing 75.2 grams of silver perchlorate dissolved in 885 grams of benzene? We notice that the word molality is used. This is the one with the L in it. We know that L is very close to M in the alphabet, so we're going to use a lowercase m, and it's going to have to do with mass on the bottom of the fraction. So our molality fraction is going to have moles of solute on the top and kilograms of solvent on the bottom. Kilograms is mass. We're given two components, 75.2 grams of silver perchlorate and 885 grams of benzene. We're not given a molecular structure of benzene, but that's not important because we have grams, and grams can easily be converted to kilograms. The first thing we have to do is figure out which is the solute and which is the solvent. The solute is what is being dissolved, and it's usually the solid. The silver perchlorate is the only one we can figure moles for in this problem anyway, so we're going to call this the solute. We have to convert the silver perchlorate into moles. When we convert 75.2 grams of silver perchlorate to moles, we divide by its molar mass of 207, and we get 0.363 moles of silver perchlorate. Benzene has to be changed to kilograms. Now, when we're changing to kilograms and grams and milliliters and liters, we don't always have to use one of these fractions. We know that kilograms is 1,000 times bigger than a gram. Therefore, we have to move the decimal point on this either to the left or to the right. That's pretty easy to figure out. If we move it to the right, we would have 885,000 kilograms. Now that's obviously way bigger than only 885 grams. So this tells us that we've moved it in the wrong direction. If we move the decimal point 3 places to the left, that's the same as dividing by 1,000. So we know that we have 0.885 kilograms of benzene. Now we're going to put our numbers into the molality equation. 0.363 divided by 0.885 equals 0.410 moles per kilogram. Problem number 19 on page 3 of your week 16 homework sheets. It reads, a gas mixture contains 45.6 grams of carbon monoxide and 899 grams of carbon dioxide. What is the mole fraction of carbon monoxide? I want you to stop and try this before you listen to the rest. So the problem asks for a mole fraction. We need to use the formula for mole fraction. Here's the formula for mole fraction. Notice that writing down the formula is an essential part of doing these chemistry problems. That is part of the credit I will give you. Writing down the formula first is required as part of the problems. The first thing that we're given is 45.6 grams of carbon monoxide and 899 grams of carbon dioxide. Both of the components need to be converted to moles. Although the question is only asking for a mole fraction of carbon monoxide, in order to find the moles of the whole solution as a total, we need to know the moles of each component. 45.6 grams of carbon monoxide divided by 28 grams of carbon monoxide, which is its molar mass, comes out to 1.63 moles of carbon monoxide. 899 grams of carbon dioxide divided by 44 grams of carbon dioxide, its molar mass, comes out to 20.4 moles of carbon dioxide. The molar fraction for carbon monoxide is the number of moles of carbon monoxide divided by the total. We add both together, make sure they're put in parentheses, comes out to 0.074. Let's look at number 6 on page 5 of your week 16 homework sheets. How many grams of benzoic acid must be dissolved in 78.1 grams of ethanol to raise the boiling point by 4 Celsius degrees? The boiling point constant for ethanol is 1.20 Celsius degrees per molal. First thing we have to do is decide what formulas are going to be needed in this particular question. The two formulas that seem obvious are the boiling point elevation formula, which says the change in the temperature, the boiling temperature equals the boiling point constant times the molal, which is molality. So we'll also need the molality formula, which is moles of solute divided by kilograms of solvent. The next thing we have to decide is, what is the question actually asking for? The question says how many grams of benzoic acid. So we're trying to find out how many grams of benzoic acid are needed here. Now, this is going to involve several conversions because neither of these formulas show grams of benzoic acid. But if we look closely at the molality formula, we have moles of solute. And it's saying that benzoic acid is what is going to be dissolved into ethanol. So benzoic acid will be the solute. We know that we can convert moles to grams using the molar mass. And they have given us the molar formula, molecular formula of benzoic acid. So let's see what numbers we can replace in these two equations. In this boiling point elevation equation, we know what the change in boiling point was. The problem tells us it's 4 Celsius degrees. It also gave us the boiling point constant. That means there's only one variable here. We can easily solve this equation by dividing both sides by 1.2. When we divide 4 by 1.2, we get 3.33. So the molality of this solution is going to be 3.33. We can take this value over to this equation now. By replacing as much as we can with numbers, we find that 3.33 molality is equal to the number of moles of benzoic acid divided by, should be kilograms of solvent, but we only have grams of solvent. Well, we can solve that problem by moving the decimal point 3 places to the left, and we'll get kilograms. Now we have one variable in this equation. The variable is moles of benzoic acid. If we multiply both sides of the equation by 0.0781, we will get benzoic acid moles by themselves, and we'll have a value for that. By multiplying both sides of the equation by 0.0781, when we multiply this side, cancels out. When we multiply this side, we get, when we multiply this side by 0.0781, we get 0.260 moles of benzoic acid. Now the question asks us how many grams of benzoic acid are required. Therefore, we have to convert moles. If we multiply by a fraction of 122 grams of benzoic acid per mole of benzoic acid, we'll find out how many grams of benzoic acid we have. Notice that this time the molar mass is on the top of the fraction and moles are on the bottom of the fraction. That's because we're starting out with units of moles, and the units of moles have to cancel out because we're looking for grams. And our final answer is 31.7 grams of benzoic acid. Number 9 on page 5 of your homework sheets for week 16 reads, what is the boiling point elevation when 11.4 grams of ammonia is dissolved in 200 grams of water? The boiling point constant for water is 0.52 Celsius degrees per molal. Again, we need the boiling point elevation equation. We also are looking at molals, so we're going to keep the molality equation. We're given the solute, which is 11.4 grams of ammonia. Now let's figure out what is the question actually asking. It wants us to find out what is the boiling point elevation. That means what is the change in boiling point. So this is the variable here that we're looking for. We have both units in order to find out the molality of the solution. We have the solute and we have the solvent. So the first thing we're going to need to do is find the molality. I have the units of ammonia, which is the solute on the top, the units of solvent on the bottom, which is water. Both of these have to be converted to new units. The ammonia has to be converted to moles. The water has to be converted to kilograms. We can start by converting the water to kilograms by moving the decimal place over 3. Now we have 0.2 kilograms. Now we have 0.2 kilograms of water. Now we're going to divide by the molar mass of ammonia. So our answer comes out to 3.35 once we've changed the grams of water to kilograms, and we divide by the molar mass of ammonia so that ammonia becomes moles. Now we have to substitute numbers into the boiling point elevation equation to figure out what is the boiling point elevation when ammonia is added to water. When we substitute numbers into this boiling point elevation equation, we find that the boiling point elevation is equal to the boiling point constant for water, 0.52 Celsius degrees per molal, times 3.35 molals. The molals cancel out. And that gives us 1.74 Celsius degrees of elevation when ammonia is added to water. Number 12 on page 6 of your week 16 homework sheets reads, how many grams of silver would have to be dissolved in 1,120 grams of ethanol to lower the freezing point by 0.25 Celsius degrees? The freezing point constant for ethanol is 1.99 Celsius degrees per molal. Again, we have two familiar equations, except this time instead of boiling point we have freezing point. Notice the equation is exactly the same, except with a little f instead of a little b. Now we need to ask ourselves, what is this question asking for? Well, it says how many grams of silver would be dissolved. So it's asking for the grams of silver, which is a solute. We know it's a solute because it's going to be dissolved. Our equations only show moles of solute, but we know that moles of solute can be converted to grams of solute. The first thing we're going to do is see which of these equations do we have most of the information for. Well, at this point we don't know moles. We don't know moles of solute. We only have the solvents numbers, so we can't use the mole equation yet. But in this equation, we know the change in temperature is 0.25 Celsius degrees, and we know the constant, so we're only missing one thing. We can solve for molality. If we divide both sides of the equation by 1.99, we find that the molality is 0.126. Now we can substitute this number into our molality equation. So we're going to substitute 0.126 for molality. We're looking for moles of silver, and we know that there are 1,120 grams of ethanol. We're going to change ethanol from grams to kilograms by moving the decimal place to the left 3 places. So now we have 1.120 kilograms of ethanol and 0.126 for the moles. If we multiply both sides by kilograms, we'll leave moles by itself. So we get 0.141 moles of silver. The question is asking us for grams of silver. Therefore, we're going to convert to grams. We multiply by the molar mass so that moles will be on the bottom and cancel one another out. We come up with 15.2 grams of silver. Let's look at problem number 13 on page 6 of week 16's homework. It reads, calculate the freezing point depression of a solution of 0.5 kilograms of ethylene glycol antifreeze in 0.5 kilograms of water. The freezing point constant for water is 1.86 Celsius degrees per mole. Again, we have these two equations that we'll be using. Let's decide which equation we're going to use first. Do we have moles of solute? Yes, we do. It tells us that we have 0.5 kilograms of antifreeze. And we do have moles of solvent, 0.5 kilograms of water. Therefore, we can find out the molality. On this side, we don't know the freezing point depression. We do know the freezing point constant, but we don't yet know the molality. So we'll have to figure out molality first. We're going to start by putting the solute on the top and the solvent on the bottom. Notice the solvent on the bottom has the correct units. The top does not. Top is in kilograms. We need to convert to moles. In order to convert to moles, we have to have grams. So we'll first move the decimal place to the right 3 spaces in order to convert from kilograms to grams. That gives us 500 grams of antifreeze. Now we need to convert to moles. We divide by the molar mass of the antifreeze to convert to moles. When we do all of the math, the molality turns out to be 16. Now we can put our numbers into the freezing point depression equation in order to find out what the freezing point depression is. We substitute 1.86 Celsius degrees per molal for the freezing point depression constant. We just found out that the molality is 16. Molal units cancel, and we multiply. The answer comes out to be that the freezing point depression of the solution is 30 Celsius degrees. That means the solution changes the freezing point so that the freezing point is lowered by 30 degrees on the Celsius scale. Notice that the degree symbol comes second in these equations and not first when you're measuring temperature. This is number 14 on page 6 of your week 16 homework. It reads, the freezing point of water is lowered to negative 0.390 degrees Celsius when 39 grams of a non-volatile molecular solute is dissolved in 475 grams of water. What is the solute's molar mass? Now, molar mass doesn't show up in either of these equations, but we do know that when we convert between grams and moles of solute, we use molar mass. Therefore, we can put it into an equation to solve for it. First, we have to figure out if we're given the change in temperature. It tells us an exact temperature of negative 39 degrees Celsius that the water is lowered to. This problem is assuming that you know what the exact freezing point of water is in Celsius degrees, which is 0. Therefore, the change in temperature is 0.39 Celsius degrees. What we don't know is the molality. So we'll solve for molality by dividing both sides of the equation by 1.86. And molality comes out to 0.21. Now we'll substitute any numbers we know into the equation for molality. So we know the molality is 0.21. We know that we have 39 grams of the solute. We have 39 grams of the solute, and we have 475 grams of water. We first have to convert water to kilograms. We move the decimal place 3 spots to the left to convert to kilograms. Now, we have to figure out what the molar mass of this particular solute is. So we're going to solve for moles. Now, in order to get molar mass by itself in this particular equation, we're going to multiply both sides by molar mass. It turns out that 0.21 times molar mass equals 82.1. Now we're going to divide both sides by 0.21. We see that molar mass is left by itself over here. When we do the math, the molar mass turns out to be 391. The molar mass turns out to be 391 grams.